Hello, my name is Rob Reynolds, and welcome to section 3.1 of calculus. Actually, this is going to be a day 2 lesson. So if you haven't watched day 1, section 3.1, go back and watch that first, where we introduced the definition of a derivative using the limit process. And we had several definitions, one of which was just finding the slope at a particular point at f at a. But I was encouraging you to use the general definition of the limit. So when I say use the limit process on your test, I would prefer and expect you to use the f of x plus h minus f of x all over h. This will give me a general solution of the tangent slope formula that you can use for any values of x. This formula, I think my math lab will have you practice a couple times, but it only finds the slope at a particular point. A little bit less helpful. So there's many ways to denote that they want you to find the derivative. This d stands for derivative of the function. That's the f with respect to x, the derivative with respect to x. Again, this is the derivative with respect to x of the function. And there's other ways to write it. This is probably the most common, sometimes just even y prime if you get lazy, but then this is the derivative at a specific point. The derivative is this is the derivative of the function evaluated at a specific point. So just recognize the different notations for finding derivatives. So let's practice a couple again using the limit process. And you may know another way to find the derivative, but I will be specifically testing you over your method of madness, the process that I need to see is the limit definition. So you're going to say, well, I could find the answer another way, much easier, much faster, and that's actually section 3.2. So I'll be testing your content knowledge over 3.1. So you'll need to demonstrate this process for me. So this right here says go to the function, and every time you see an x, plug in x plus h. So we're going to go right here to the function, and we're going to replace this with the square root of x plus h. That is going to the function, this function right up here, and instead of writing x, the square root of x, we wrote the square root of x plus h. Then we go minus the function, and I've always encouraged you to put parentheses around that so you don't forget to distribute, but honestly, there's nothing to distribute because it's just minus one term. But if there was more than one term, then you would have to distribute the negative. So now you may ask, well, how do I take the limit of that? I can't do direct substitution because if I try to plug in a 0, I'm dividing by 0, and that simply won't work. So the answer is the conjugate. So we're going to take this and multiply by a unique value of 1 that will help us rationalize not the denominator, but rationalize the numerator. So conjugate means change that middle sign. So everything that I just wrote here in blue is just the value of 1, and so we're not going to change the value of the fraction. It's going to look different, but it's going to help us hopefully cancel the h so we can do some direct substitution. So let's FOIL this out. First terms, the outer and the inner will cancel. That's the meaning of conjugate. So I have x plus h minus x over h times the x plus h square root of h. And I still have that limit out there, and I would hang on to that so you don't forget to just evaluate it at 0 when all is said and done. So this becomes h over h times the quantity x plus h plus the square root of x. And finally, we can cancel the h, leaving me with just evaluating the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x, which of course is just 1 over the square root of x plus the square root of x, because again, we're going to let h be 0. And the final answer is 1 over 2 square roots of x. Now there's a part B up here that says, well, okay, that's fine, but go ahead and find the equation of the tangent line at this point 4, 2. So again, this is that slope formula that I keep talking about, the slope of the tangent line formula for all values of x. This is the general equation. Of course, we want the point 4, 2. So we're going to let x be 4 to evaluate the slope. And of course, that's just going to be 1/4. Then we'll go ahead and write the equation. Y equals 1/4 x plus b. And we've got a y value. There's an x and there's a y, so I'll just plug it in. 2 is equal to 1/4 times 4 plus b. And b turns out to be 1. So I'll write the equation. Y is equal to the 1/4 x plus 1. And sure enough, this is what the author has as well. And this is a good representation. Here comes the function. Here's that point. And again, what we're doing is finding the slope of the line tangent, the equation of this line right here, that's tangent. And with that, we can do all sorts of physics calculations, and we'll get to why that's derivative, or the slope of the tangent line, is so important in math. Here comes another example. So again, we'll follow this process. The limit as h goes to 0 of f of x plus h minus f of x all over h. In this case, it's the limit as h goes to 0. Go to the function and plug in x plus h minus the entire function. Well, again, nothing to distribute here. All divided by h. Last problem, the concept was simplifying the conjugate. In this one, I think we're just going to have to subtract by finding common denominators. So up top, I've got a denominator of x plus h quantity squared, and I'm going to multiply that by t squared. This one, top and bottom, gets multiplied by t squared, and I bring over a t squared. But this denominator here is lacking a lot. It's the x plus h quantity squared and the x plus h quantity squared, which is really that square double square rule. And then, oh, I got to distribute. Well, I think there are no x's in this problem. Everything's a t, so I'll get rid of those x's because they were confusing me. So these are t's plus h's is the variable, g at t instead of g at x. So I apologize for that. But then I've got minus t squared minus 2th minus h squared. Hope those x's didn't mess me up, but there really is no x in this problem. Now, let's not forget about this little h down here. Instead of taking a fraction divided by a fraction, I can actually just keep him and just multiply by 1 over h so that I don't have a compound fraction. And that's kind of nice because I can actually factor out an h from up top, leaving me with negative 2t minus h. And then, fortunately, this h will cancel with this h, and that I think is very helpful when I'm trying to evaluate the limit as h equals 0. So I'm going to let h be 0. Maybe I should rewrite this because it's getting a little complicated, and I would encourage you to do likewise because when I'm grading your tests, I need to try to make sense of everything that's being canceled. So make sure that it's somewhat understandable for me. So if I go ahead and let every h be 0, I'll have negative 2t over, now this is interesting, this is t squared and t squared are t to the 4th, which by the way is just negative 2 over t cubed. And this is the formula that I'm going to use to find the slope at any given t value instead of an x value. But that's all they asked me for. They didn't ask me to write the equation of the line, so I think I'm done with this problem. They just said, what's the derivative, which is the slope formula. That's tangent, and that's it. So good. Negative 2 over t cubed. The last part of this video, we're going to practice given a function and sketching the graph of the derivative. Now, remember, this is just testing to see if you understand that derivative really means the slope of the tangent line. So remember, the derivative is nothing more than the slope. So let's go find the slope of this thing. The slope of this line between -5 and -2 looks to be, well, rise or run, or rise down -1 and run 1. Looks to be -1. So the directions say sketch a graph of the derivative. So, and the derivative's at -1. So I'm off my graph, and it looks like it's -1. If I could plot the y value of -1, it's down here. Well, be careful. It only goes to about right here, because it looks like my slope is going to change. Well, -2, that is. So it looks like my slope now between -2 and 0 is +1. So I'll graph the slope of +1. It's just constant, a nice horizontal constant line between -2 and 0. And this green, I've already used green, so we'll go this maroon. Slope looks like it's down 1, run 2. So that's probably at a half. And it's negative because it's sloping down to the right. And so that's your first look at the graph of the derivative function. It's these horizontal lines here. And this is how the author depicted it. They draw a little bit better than I do. So it gets a little bit more confusing when I have a curve and they're not nice straight lines, but we can still find and sketch a graph of the derivative function. And one of the most helpful tips that I think I can give to you is locating where the slopes are 0. Because if the slope is 0, that means that the derivative is at 0. And so every time you find a horizontal slope 0, you know that it's going to cross the x-axis at that point. So I'm going to locate 3 every time there's a max and a min on a function, then that creates a 0 for the derivative. Now the next thing I notice is that here the slope is positive because the function, if I were just to graph this line, it's called the tangent line to any given point, it would be positive. And if it's positive, then I know that the graph is up here in this yellow section. And when the slope is negative, like in this green, because it's coming down, you know what, like when you're skiing and you're skiing downhill, that's slope negative, then I'll be below the axis. Now, be real careful, because even though the function right here is increasing, I want you to be careful, because the slope is decreasing, because see how it keeps getting closer and closer to 0. So it's the slope starts out really high, like it's really steep down here, and then as I move, even though the function is increasing, going up, the slope is decreasing. Let me say it one more time. The function is increasing, but the slope is decreasing, and that's difficult for students to understand. So if the slope is decreasing, then that means that the derivative is decreasing. So that maybe this purple is the derivative, because it starts out really steep and then it kind of swoops down to a 0. Then in this green section, notice that, well, about halfway, the slope starts out at 0 and it gets steeper, steeper, steeper. And then about halfway through, it starts getting closer and closer to 0 again. So it starts getting steep and then approaches 0. And that change happens about halfway through. And this is actually called an inflection point, which we'll study more about later. But we know something interesting is happening about halfway through. And what does that mean? Well, it's negative the whole time. See how this whole, since the function is decreasing, the slope is decreasing here as well, but it's approaching 0 again at this point, -1. So that's why at this inflection point you hit 0 for a derivative. I don't know if I'm explaining this very well, but I'll try one more time. Here the function is increasing, but notice once again that the slope is decreasing because it starts out going up here. There's kind of another inflection point. It kind of looks like halfway between. It's pretty steep. Another inflection point, and then it's starting to go back to 0 again, and then it gets really steep again. And in this part, I'll highlight it in blue. It looks like it's going to go negative again. So there's your first look. So I would maybe come down here. First look at a graph of the derivative function. And again, you're welcome to read how the author explains this. This slide is just talking about if it's differentiable, then we assume that that implies that the function is continuous. If it's not continuous, then we say it's not differentiable. And remember, it's also not differentiable because at a cusp right here, because the limit from the left does not equal the limit from the right. No gaps are allowed. Does not exist at infinity. So see how, again, the slope exists here and here and here. But then it starts getting so steep that, well, you know what the slope of this line is. The slope of the vertical line is no slope. You can't take the slope. So when the function looks like this S on its side, somewhere in here, there's a vertical line that here's the slope of the tangent line, the slope of the tangent line, the slope of the tangent line, and somewhere it turns vertical. And again, there's no slope at vertical lines. Vertical lines have no slope, they're undefined. So we'll end the video with just this last little exercise. I'll focus in on just sketching the derivative of this thing, and it looks like the function is going to kind of be increasing between -4 and -2, but notice that the slope is, well, I don't know, it depends on, do you think it's pretty constant? It looks like it's kind of increasing a little bit. Like here, the slope of the tangent line, it looks like it's a little bit steeper here. And it's positive, so I would say it looks pretty similar to what it's doing. I mean, it might be a straight line, but it might have a little curvature to it. So there's some subject to, I'm going to draw it just pretty similar to what the function looks like. It looks like the function is increasing and the slope is slightly, because here the slope of the tangent line and then here the slope of the tangent line looks like it's a little bit steeper. I'll probably just put an open dot here because I don't really know what the slope is happening at that particular point. I just won't define it. So this next little section looks like it starts close to 0 and it gets pretty steep. So I'll start at 0 again. I'll put an open dot, and it gets steep like in a negative, the slope. So not only is this function decreasing, but the slope is negatives, and it gets really steep, like going to infinity. So maybe there's even an asymptote here. It's approaching something that's really steep, and it's going negative. Now over on this side, it's also infinity. It's just like so almost, gosh, it's just probably undefined there. It's probably, that's why, in fact, it is vertical line. But but this is positive slope, and it's that positive slope. Remember, is up here. It's up in this yellow section, where the negative slopes are down here in the blue section. So I need to start up really high for this next section, and then it approaches, there's a slope of 0. So I need to start up really high and maybe come on down to a 0 for this next piece. So far it's kind of confusing what's the, let's see if I can bring this to life for you. So far I've got the derivative is this, and this. is what I'm looking at for my derivative function so far. And then the last little piece that I need to worry about is this guy right here. And I see that the slope starts at 0, and it looks like it's getting pretty steep again. Steep as in going down. So maybe there's like a little twist in here or something, but I think it would look something like this, where it's getting, that's a high negative number. And if I remember correctly, I think the author kind of took a little bit different spin. See how the author kind of went off and kind of almost looks like it's almost leveling, and I just disagree with that. So again, I'll have to have some flexibility in how I grade this, but I really think it should be not going off into the A direction, but it should be kind of going off into the B direction. So that's the end of section 3.1. If you have any questions, feel free to email me with your questions.